Hi, so let's talk a little bit about electric charge and force, a crash course in electrostatics. Electrostatics. So this is static electricity, we normally call it. And so it's just electrons that aren't moving, although we'll see them jump from one object to another. And you're familiar with this. If you take a balloon and you rub it on your hair, and then when you hold it above your hair is attracted to it. And so this is electrostatics. So we're going to talk a little bit about what's going on here. So basically it's just a shift of electrons. When you rub against your hair, that friction, you have the two materials. What happens is we have some electrons which will jump over into one of the materials. And it's dependent upon the type of material that you're using. And so what you'll end up with is on this material on this side, so say, I don't know, the balloon. The balloon would end up with, that still has some positive charges. One note, so it does have negative charge electrons. That's the symbol for an electron. So you still have some positive charges, and normally it would be equaled out, but now you have a bunch of excess negatives. And over here, you still have the same number of positives, but you've lost 3 electrons. And so this one has a shortage of electrons, so we would say that it has a positive charge. And this one has excess electrons, so it has a negative charge. And so a positive charge indicates an electron deficit, and a negative charge indicates an electron abundance. I lost the word. Excess. Let's use that. So an excess of electrons. And the idea here is that it's the electrons that get moved. So it's movement of electrons. Movement of electrons. Inside of the material, you have the protons, which have positive charge, and the electrons, they have the negative. The protons we can't move. Those are inside the nucleus of the atom. So let's look a little bit at the inside. So in the inside of the atom, you're going to have some protons and some neutrons. The protons have a positive charge on them, and neutrons don't have any charge. So you might have something like this. And then skimming around the outside, you have these negatively charged electrons. And these are the things that get knocked off. And there's certain materials in which we can knock off the electrons a little easier, and these are called conductors. So they have these free electrons on the outside that are able to move around. Versus insulators, where the electrons are held very tightly to the nucleus, and so it's hard to move them. So that's as opposed to insulators. So conductors are things like copper and gold. AU? I can't remember, AU or AG. Here, I'll just write gold. How's that? Okay, so we use these for electrical wire because they're good conductors. Insulators, that would be like plastic, glass is a good insulator. Air is a good insulator. Alright, so it's all about moving electrons. Now the behavior of it, so we have interactions between charged objects. So let's say we have 2 objects. One has an excess positives, so it has a positive charge, and one has excess negative. Okay, so since we have a positive charge and a negative charge, these things will attract each other. So we can say that opposites, just like in magnetism, opposites attract. Likewise, if we have, or similarly, if we have a positive charge and a positive charge, those are going to repel each other. So like repel. But what if we had a positive charge, excess positive charge, and a neutral object? So the net charge was 0. You had like 2 positives and 2 negatives. So the net 0. Well, these in fact would attract each other. So neutrals attract. Neutral is attracted. My handwriting is terrible today. Is attracted. And this is also works with a negative charge. So if we had an excess negative charge and another neutral, we would also see an attractive force. So neutral objects are attracted, always attracted, to a charged object. So why? Why does this happen? Well, we have to think, let's say I have a heavily charged object. So we'll put a bunch of negative charge on here. And let's say I had a neutral object. I'm going to make it like this just so that we can show. And this is very far away. Okay, so we're going to move this into the picture. When we move this close, originally we would have something like let me draw, this is before. So since it's neutral, you would have like positive, negative, positive, negative, positive. You know, you'd have the same number, but they would be scattered throughout the material. When you bring this close, this negative charge, it's going to pull all of the positive charges. If this is a conductor, it will pull all the positive charges towards one end, and it's going to repel all the negatives, in essence. And so you get this separation of charges. And so in effect, we end up with a net pull on it, as this one's being repelled. And so this is called polarization. Polarization. We've polarized the charges on this. Now, one of the interesting things we can do is we can take a neutral object like this, bring a charged object, but not touch it. Just bring it close to it, so we get this neutral charge, and then touch another object to it. So now if I touch this object to it, some of these are going to jump across, and we would end up with a net charge on both of these. And that's charging by induction. So we'll talk a little bit, I'll clear this, and then we'll talk a little bit about charging up objects. Okay, so let's look at charging objects through induction. So induced charge. Induced charge. Oops, what was that? Hold on a sec. Alright, so induced charge. This is as opposed to the friction. So we can charge through friction, or we can charge through induction. So that's what we're going to talk. We're going to induce a charge, and it's what I was just talking about. So if we have something with a lot of charge on it, so let's give it a whole bunch of positive charge. So we have excess positive charge here. There's still negatives on here, but we have more positives. And then we bring a neutral object close to it. Let's just say, I don't know, a big metal sphere. So we bring a metal sphere near it. What it's going to do is it's going to pull all the negatives to one side and push the positives to the other side. And then we bring a second sphere, and we're going to actually touch them. So induction is going to require some touching. So remember, this was neutral to begin with. Once I touch it, then what's going to happen is we're going to get a polarization across the entire thing. So these positive charges are going to move way over here, plus the positive charges that existed on this sphere. And then the negative charges are going to move over here and join these. And so these are now moved over here. So we end up with this polarized object. And now when I pull this away, what we end up with is we have a negative charged object and a positive charged object. So induced charges, those lead to, first you got to have contact. You must have contact. And they lead to opposite charged objects. Opposite charged objects. Alright, so the last thing that we need to talk about with electrostatics is, like, these are now two charged objects, and we know that they're different, so they're going to attract each other. and we want to talk about the actual force of that attraction. And it's very similar to gravity, except it can either be repulsive or attractive. So the force of attraction. And this is straight off of your equation sheet. Let me pull that over so you can see. So we're looking right here. These are the equations that we'll use for electricity. Electrostatics is this one. And then we'll start electricity. And that's the rest of these. So anyway, we're looking at this one right there. And so what we see is that the electric force, so the force between charged particles is equal to K, which is a constant. It's on your equation sheet. It's a number. And then we have the charge of one object times the charge of the second object, and we make it absolute value. I'll talk about that in a second, divided by the distance between them squared. So it looks just like gravity. These are the charges of the objects. And this is the distance between them. Okay, so charges on the objects. Now we make it absolute because we don't know the direction. So you have to determine the direction by the types of charges. So the net force, this one on this one would be positive in this case. If I were talking about two like charges on each other, then they would be repelling. So I would make like the force of this on this would be in the negative direction. So we use the absolute just to show that we don't know what the sign is. So that's your big equation. The other thing to know, and this goes back to just when we charge objects, is that the charge itself, Q, is usually given in number of electrons. So you could have like a positive 2e, and so that's an electron, charge on an electron. The charge on an electron and a proton are the same, just one's positive, one's negative. So we do it in multiples of e. The other thing to know is that it's quantized. What that means is that it's 1, 2, 3. There's no in between. It's integers only. You can only have one electron, 2 electrons. Electron is a fundamental particle, so there's nothing smaller than that. So we leap, and that has to do with just an electron moving from one object to another. And I think that about covers it. So being able to determine the force, being able to talk about how objects are induced, definitely knowing that their E is a fundamental unit, the electron. The column, the units on this are coulombs. It's a big C. Coulombs. That's an O. I cannot write today. Coulombs. Okay. Here, I'll write it down here big. It's coulombs. Messed up. C-O-U-L-O-M-B-S. I think that's how you spell it. Coulombs. Anyway, that's it for electrostatics.